Okay, now we're going to talk about three basic types of graphs that we're going to be looking at in physics class. So one type we've already talked about, and that's linear. We're going to talk a little bit more about that type of graph. We're also going to talk about quadratic and inverse graphs and what those graphs look like. So let's talk about linear again first. So the example we used for a linear graph before was if we measure the mass of physics dog as she is growing. If we increase the mass of physics dog and measure the amount that the spring stretches, we found that that was a linear relationship. The bigger the mass, the more the spring stretched. So when we talk about a linear relationship, the equation for something like that is in this general format: y equals mx plus b. So here y is whatever you put on your y-axis. So in this case, it was the amount that the spring stretched. So that's your y value. M stands for slope, so that's the slope of your graph. And x is whatever you put on your x-axis. In this case, that was our mass, and then b is the y-intercept. So in this case, the y-intercept was 0. So let's just go back and review what that graph looked like. So this is what that graph looked like. We had a linear slope. Looks like a straight line, and our equation worked out to be y equals 2.0167 times x. And then, because we don't have another term here, that means that our y-intercept for this graph was 0. So here, this was the amount that the spring stretched. So we'll call this length stretched. Equals the slope times the mass. That's what was on our x-axis. And then our y-intercept was 0, so plus 0. So let's just check our data and make sure that it fits with this equation. So if we plug, first of all, if we look at what our slope is in our graph, that was approximately 2. So we're just going to say that that's 2. We're going to round that off to one significant figure. So for this particular set of data, our equation would be y, or the length stretched, is equal to 2 times x, or 2 times the mass. Simple enough. So looking at our data, our mass multiplied by 2 should equal the length stretched. So 1 times 2 is 2. Our second x value was 2. So if we multiply that by 2 in our equation, 2 times 2 is equal to 4. So we see that that's almost what we got. Our third x value is 3. 3 times 2 is 6. So that's almost 6. So again, because these were measured values, they're not going to be exactly fitting with our theoretical model, and that's why these points aren't exactly on the line. And that's okay, because every time you measure things, you have some slight variation in your measurements. That's just what happens. We're just looking at the overall trend. So to summarize, a linear graph should look something like this. Now you might have a steeper slope or less steep slope, but it's going to be a straight line. Okay, the second type of graph is going to be quadratic. So let's talk about quadratic. So one example where you might see a quadratic relationship is if you're measuring how far something is falling in a given amount of time. So let's say this is physics dog is jumping off a dock, going after a frisbee, and she's going to land in the water. So if we measure how much time she's in the air, the distance that she falls is going to be related to the time squared. So for a quadratic function, the general equation looks something like this: y equals ax squared plus bx plus c, where a, b, and c are just numbers, constants. So for this type of equation, generally, the thing you want to focus on is just to see that y is proportional to x squared. So these other terms are going to determine some other details about the graph, but the fact that y is proportional to x squared means that the general shape of the graph is going to look something like this. It's going to look like a parabola. Now, if we had our other quadrant over here, we would see that it goes back up the other side symmetrically. But in physics, we generally are only going to be using the first quadrant. So this bx and the c term determine things like how far this is stretched out, or where it hits the y or the x-axis. But what I want you to focus on is that this x squared here determines the fact that this is a parabolic shape. So let's look at this in Microsoft Excel. I've put some data in here already that is related by a quadratic equation. So here we measure our times every 0.5 seconds, and then we measured the distance that physics dog had fallen in that amount of time. And if we make a graph for these, it looks like this. In fact, let's go back and remake this so you can see how. So we were going to select our data, go to Insert, we're going to choose Scatter, and that gives us our points. So then if we want to look at the relationship, we can right-click on our points, go to Add Trend Line. So let's move our graph over here so we can see a little better. Now, if it defaults to the linear, oops, let's click back on our trend line, we see that that doesn't fit this data set very well at all. So we want to try something different. If you click on power, now it fits very nicely. So if we display the equation on the chart, we should expect to see something where y is equal to something times x squared, with possibly a couple other factors. So I displayed the equation, and it turns out y is equal to 5 times x squared. And that's exactly what we would predict to see for a quadratic relationship. Y equals 5x squared. The third type of graph we're going to look at is inverse. So an inverse relationship might happen if we have, say, physics dog is on a cart and we're pushing with a constant push, let's say 20 units of pushing force. And we want to measure how fast does physics dog speed up. So that's actually called acceleration. We'll be talking a lot more about that. So what we're going to do is add mass to the cart, push with the same amount of force, and see how quickly we speed up. Then we're going to add some more mass, push with the same amount of force we did before, and now measure how quickly we speed up. And hopefully common sense should tell you that the more mass you add, the more difficult it is to speed up, or the longer it's going to take to speed up. So the more mass we put on here, the less acceleration we get. So this type of relationship is in this general formula, y equals a over x. So in this case, our y value, or our dependent variable, would be acceleration. A is a constant value. So in this example, our constant value was our push, which was 20 units of force. And then our x value was mass. We were adding mass. So if we go into Excel and we look at what this type of graph looks like, here I've set up some data. So if we select this data, go into Insert, Scatter, we see a third type of shape that we haven't seen before. So this looks a lot like the power, or the quadratic, but it's going the other direction. So instead of y increasing as x increases, y is decreasing as x is increasing. So if we add a trend line here, we see linear doesn't fit very well at all. So there's no option to choose inverse. So we're actually going to choose power. And let's display the equation on the chart. Okay, so here's our equation. It says y equals 20x to the negative 1. y equals 20 times x to the negative 1. So let's analyze that a little bit. So from Excel, it gave us this equation. Now, if you remember from math class, x to the negative 1 is really the same thing as saying 1 divided by x, or 1 over x. So we could also write this as y equals 20 times 1 over x, or y equals 20 over x, if we combine the 20 times 1. And so then we see that that looks exactly like the equation that we started with, where acceleration was our y value, 20 was our constant, and x was our mass. So it matches up. So in general, an inverse graph should look something like this. One thing I want to say about inverse does not look like this. So this is not an inverse graph. And a lot of people want to say that this is inverse. But this is really just a linear graph with a negative slope. So this would be something like y equals negative mx plus b, where this m is a negative value. And that's what causes the line to slope down the other way. This is different from inverse. Inverse is where y is equal to some number divided by x, and that gives you a shape like this. So those were the three basic types. To sum up, we had a linear graph, which looks like this. We had quadratic, which looks like a curve sloping upward, and we had inverse, which looks like a curve sloping downward.